Okay, you can begin.
Okay, I just passed out to class two documents. The first is a one-page syllabus for the course that we'll be going through momentarily. The second is a one-page introduction, which we will also be going through. So let's begin with the course syllabus. It's in the typical ABET format for a course syllabus. What we've got there is the course number and title and semester, followed by the course description. This is the same course description that you'll find online and in the course catalog for the university. Note the prerequisites for this course. There aren't too many of them. 3300, which is electronics, and 3470, which is fields and waves. Those are the only assumed prerequisites for the course. We'll be making a lot of use of ideas from fields and waves. So make sure you're up to date on your fields and waves material. The electronics material, not so much. We'll point out for you where electronics comes into play. The rest of the course description is a description of what we're going to be talking about during the semester. Scattering parameters, matching networks, and the Smith chart. We'll be making a lot of use of the Smith chart in this course. I'll have a lot more to say about that. Stability considerations for design of high-frequency amplifiers. It turns out you have to pay an awful lot of attention to stability when designing amplifiers to operate at high frequencies. Different design techniques to meet varying design criteria that you might have for your high-frequency amplifier. Design techniques for low noise design, broadband amplifier design, high-power amp design. We'll also touch on the topic of RF oscillator design, closely related to amplifier design. And throughout the entire course, we'll be making a lot of use of computer-aided design techniques, software packages, primarily Agilent's ADS software that some of you may be familiar with already from use from other courses. However, I'm not assuming anybody has any previous experience with the software that we're going to be using. So prior experience with ADS is not necessary. I'll be teaching you everything you need to know about it in the during the course of the semester. All right, there's a textbook for the class. It's this one right here, Microwave Transistor Amplifiers, Analysis and Design, second edition. Make sure you get your hands on the second edition. It's greatly modified and expanded from the first edition. It's not all that new. The second edition came out in '97. A lot of people are waiting with bated breath for Gonzalez to come out with a third edition. Hasn't happened yet, so we're making use of the most recent edition available. This book is a standard in the field. This is the Bible for microwave amplifier design. It's used widely throughout the country, throughout the world, as a matter of fact, as a textbook for this type of course. As a matter of fact, it's such a standard in the field that if you get a job in RF design, and if you haven't had a course in RF amplifier design, or for some reason if you don't have a copy of Gonzalez, I know of several companies that one of the first things that they do after they find you a desk and set up your cubicle at that company is they order you a copy of this book to put there on your shelf to use as a reference on the job. Very good book to have. So for that reason, I would urge you very strongly, get your hands on this book. It's a little pricey because of all the fancy figures and equations and so on, but it's well worth it if you end up in a field that's in any way related to RF design. Not only that, but I'll be assigning a lot of problems straight out of the textbook here. So for purposes of solving homework exercises, you're going to want a copy of the book. Also, I'm going to describe this in just a moment. I'm going to have some fairly detailed class notes that we're going to be going through during the semester. But the class notes are no substitute for the textbook. The class notes are based on the textbook and go through the material in the textbook, following the book's organization and topics and so on, but only very briefly in those class notes. If you want more details, the first thing I do is I refer you to the book, and I say, read up on that section of the book that talks about the material from the class notes. Also, the book contains a wealth of exercises and examples, fully worked out examples. I'm not going to be doing all that many examples here in class. And if you want to see more examples, let's say for help in doing homework problems or for purposes of studying for a test, and so on, the textbook is a great place to go. Those problems are worked out in a lot of detail. You'll find several problems on each and every topic worked out in full detail, as I say. Now, as I just mentioned, I also have class notes, and I'll be going through the class notes here in PDF format. I'll be just flashing them up here on the screen and going through them throughout the semester. Those class notes are available to you on Blackboard. There's a Blackboard website that I've set up for this course in particular. And if you're enrolled in the course, all you have to do is put in your username and password, the same one you use for any FAU computer login, and click on 5371, and you'll find various sections there that the Blackboard website is divided into, such as homework assignments, examples, and then another section is labeled class notes. And in the section labeled class notes, you'll find in that folder the class notes themselves in PDF format. Download them, print them out. I'll be going through those class notes page by page, and that's what I'm basing my lectures on. Right now, you'll find the Chapter 1 class notes available on Blackboard. There will be in all probably 5 chapters worth of class notes. The subsequent chapters after Chapter 1, they'll be available as soon as I get through editing them, which will be before we need them for use here in class. I continually update these class notes, and you'll see me this semester spotting new errors and making new notations in my class notes up here for inclusion in the next version of the class notes that I use next time I teach the course. Okay, log on to that website. Under the folder that's called Course Information, you'll find this very syllabus, which you can download and print out as many copies as you'd like. Now, I've already talked about this. We're going to be doing a lot of computer assignments in this class. Mostly, I say Hewlett-Packard's. It's actually Agilent now. They've spun off their software division. It's now called Agilent. ADS. ADS stands for Advanced Design System. We have a site license for ADS on the networked computers in room 345 of the Science and Engineering Building. The Science and Engineering Building Computer Lab. Most of you, I'm sure, are familiar with that computer lab. It's used for an awful lot of the classes in engineering here at FAU. The site license is only for those machines in 345. There are other computer labs on campus, like Business 109 is a big computer lab, and there's several others located elsewhere on campus. You can't run ADS on those computers. You've got to truck over to Science and Engineering Building, room 345. I've had in the past a number of students ask, is there a light version of ADS available that I can download and put on my own PC? Unfortunately, the answer there is no. There's no ADS Lite that you can download and make use of at home. So in order to work these computer exercises, you've got to make it to room 345 in the Science and Engineering Building. Some of you who are employed, your employer may have ADS. Find out. The only other alternative would be for you to buy a license, a single-user license, for ADS for yourself. However, let me warn you, that's a pricey proposition. We're talking over $1,000 for a copy of ADS. Okay. Next is my information, my name, office location in the Science and Engineering Building on the 4th floor there. It's a couple doors down from the EE office. My phone number here on campus, I have phone mail. So if I don't answer the phone, you can always leave a message. And I can access my phone mail from off campus, although I must say I don't do that very often. Maybe if I'm out of town for an extended period, I might pick up my messages from the office. If you need to get in touch with me and get a quick turnaround time, and I'm not in my office or not answering my phone, the very best way to get in touch is by using my email, my FAU email. There's the email address. Don't lose that one. I, of course, have my email program running on campus whenever I'm here on campus. I also almost always have that program running at home 24/7 on my PC at home. And every now and then I'll hear a little bring, and I'll wander over my computer and see who sent me a message and what it is, and if it's important enough for me to interrupt what I'm doing, like watching an important TV show or something, to answer that email. So you can get in touch with me an awful lot of other times by getting in touch by email. And if you need a face-to-face and can't find me on campus or in my office, give me a call or send me an email and we'll set up a time to meet. Doesn't necessarily have to be during my regularly scheduled office hours. But talk about office hours. Here's what they are for summer semester. 1 to 2 p.m. Mondays through Thursdays. Those are times when I am guaranteed to be found in my office, ready and waiting for you to come visit and ask me questions concerning this class or concerning anything else that you'd like to talk with me about. Of course, I'm on campus and in my office an awful lot more time than you'll see right there listed as my office hours. So feel free to, knock on my door and see if I'm around and see if I'll talk to you at other times. Chances are I will. Sometimes, though, I might have to tell you, sorry, I'm in the process of preparing for an important meeting, or sorry, I'm in the process of meeting with one of my graduate students or something of that sort, and might have to turn you away. But more often than not, if you find me in the office, I'll be able and willing to talk to you at a lot of other times other than these posted office hours. Next is the studio time and location. If you're here, of course, you know this information. If you're in the distance learning section, and by the way, I may want to talk about this right now. If you're in section 3, the distance learning section, you're going to need to show up. Wait a second. I take that back. You aren't going to need to show up. If you're in section 2, the library section, you are going to have to show up for tests at the very least. When I first drew this thing up, the end of last semester, I didn't know what studio we were in yet. We're in Studio 3, so put down IS3. Make sure you know which studio we're meeting in over here in Instructional Services, IS Studio 3. Let me talk about the different sections for this class. This is just like any FEEDS course. This is a course that has 3 sections. There's Section 1, Section 2, and Section 3. Section 1 is the normal classroom section. Those are students who sign up to take the course as a normal class. They show up during the normally scheduled class time every Tuesday and Thursday at 9:45. Section 2 is the so-called library section. Section 2 is a section where you can take this course sort of like on almost like an independent study basis. It's not really independent study. People who are enrolled in Section 2 don't have to attend the lectures. What they do instead is they go to the library twice a week and check out a CD that has the recorded lecture on it and view that lecture on the CD. Section 3 is the distance learning section. That's the section for folks who are in the FEEDS program, formally enrolled in the FEEDS program, full-time employed people who are working on their degree through the FEEDS program. And in most cases, they view lectures either by looking at CDs that are physically delivered to their place of work, or they view lectures as streaming video over the internet. So those are the three sections. For purposes of assignments, there are really no differences. When I assign an assignment, the document containing the assignment is on Blackboard, and people in all three sections can access that assignment immediately. As far as due dates are concerned, the due dates are the same. However, for people who are in the library section or in the distance learning section, I may not receive that assignment until a day or two later because of the delivery time involved. But it's time-stamped. So if you have it done on time and you turn it into the coordinator in the library, or you turn it into the coordinator at your work site, if you happen to be in sections 2 or 3, they'll timestamp it saying it was turned in to me on time, and they'll go about delivering it to me. It'll make it to me within a day or two. As far as tests are concerned, people who are in the library section, section 2, have to come here physically to the classroom to take the test on the days that the tests are given. So you folks who are here in class right now, you'll be seeing the library people on the test dates as well, coming here to class. For those of you who are in the distance learning section, section 3, you'll be taking the test on site wherever you happen to be located, proctored, of course, but taking it on site. It'll be sent to your proctor. You'll meet with your proctor, sit down and take the test for the normal amount of time that everybody else in the class has for the test. And you'll turn it in to your proctor, who will then timestamp it and send it off to me. The key fact to be aware of here, those of you who are looking at CDs of this lecture in the library, you have to be here the 3 days that I'm giving the 3 tests for the class. Don't have to be here for any of the lectures, but those 3 tests you do. Okay, goals. Well, this is just sort of a lofty statement of the goals of the course. You'll have a better understanding of what these goals entail as we work our way through the semester. Topics in the course. Well, to get this list of topics, what I basically did is I looked at the table of contents of the book and said, we're going to be basically covering the first 5 chapters of the textbook, plus a couple of added things, including software and things of that nature. So the list of topics here is basically following the table of contents of the textbook with 1 or 2 extra topics added in. All right, how about grading for the course? I'm going to, by the end of the semester, come up with an overall final percentage for each student in the course. An overall final percentage between 0 and 100%. And here's how I come up with that percentage. what I'm going to do is I'm going to total up all the points for homework assignments and weight that as 15% of the final total. I'm going to add up all of the scores for computer assignments and weight that as 25% of the final total. And then I'm going to take each student's scores on the 3 exams, the 3 class tests that we're going to have during the semester, and weight each of those tests as worth 20% of the final total. Then add them all up together with the weights shown here and come up with an overall final percentage for every student in the class, and assign letter grades based on those percentages. You'll note that I actually wrote down dates here for the 3 semester tests. You can go ahead and put those dates, mark them on your calendar right now. Those dates aren't going to change. I'll test on the material that we've covered up to that date. I won't say, well, wait until we finish this chapter until we give a test or something like that. I'll be giving the tests on those dates. The 12th, I think, is a Tuesday, the 12th of June. The 12th of July is a Thursday. I think August 9th is a Thursday as well. Remember, for summer semester, there's no finals week. Classes go through Friday, August 10th. This is the last day of our semester, Thursday, August 9th, for this class. And so that's how I'm going to be coming up with the overall final percentages for grading. Now, homework assignments worth 15%. That's a decent percentage. It's not real large and it's not real small. You'll find that we have more homework assignments during the first portion of the semester than we do during the later portion of the semester, primarily because we're going to have more computer assignments towards the end of the semester. And so I'm going to try not to overload you by giving you too many homework assignments and computer projects at the same time. Computer projects, that's worth a lot. That's 25%. There will be probably 5 or 6 computer assignments that I'll be giving during the semester. And I'll total them all up together and give that a weight of 25%. So the computer assignments are worth quite a bit in this class. The semester exams, all 3 of them, they're all the same, all worth 20%. There is no final exam. That 3rd test is just test number 3. It just covers material that we've had since test number 2. It's not cumulative or comprehensive or anything else. I'll just treat it like a normal test, and it'll have the same ground rules and the same format as a normal test would have. As far as testing is concerned, let me say a word or two about that. Tests will be open book and open notes. Okay? So you'll have available to you the textbook, another good reason to buy this thing. Bring it in with you for the test, and bring in your class notes And bring in any other references you might want to bring along. Bring along your homework assignments and my solutions to the homework assignments. And bring along computer assignments and bring along tests. Bring along whatever you'd like. Other books. Other people's notes. I don't care. Whatever you want. Fair game. Open book, open notes. The other thing is, you're going to find that for most of the tests, probably all of them, that you're going to be needing to use Smith charts. I'll be making Smith charts available, but you're going to have to be responsible for a compass and a straight edge to be able to use with those Smith charts. So here's a little advanced warning. Get yourself a good compass and straight edge to use along with the Smith charts. Also, you're going to want a calculator at the very least. I say at the very least because some of you may have laptops that you use. If you want to use a laptop during a test, feel free. If you're feeling left out because you don't have a laptop and someone else next to you is using a laptop during the test, you can always go to the library and check one out. Did you know that? I only heard about that a couple of months ago. You can go to the library and check a laptop out. So anyway, all the computing power you want. Open book, open notes, whatever you can muster as far as computing power is concerned. Okay, let me see. Anything else I wanted to bring up here? Oh, yeah, there's one thing students always worry about. I don't know why. Okay, I come up with this final percentage. So far, so good. How do I decide who gets what letter grade? Here's the very worst case possible scenario. Okay, so there's the idea. I'm going to place cutoffs for the final percentages once I compute them, and then assign letter grades based on what range each student's final percentage ends up in. And this is the very worst case scenario. This is the strictest I would possibly be at the end of the semester. It's a straight scale. I'm not curving anything. I'm saying that anybody with an 85 percentage for their final percentage or better is going to get something in the A range. 75 to 84, guaranteed to be a B. 65 to 74, guaranteed C, and so on and so forth. But of course, you don't want to be one of those so on and so forths. I say that's the worst case possible scenario because I'm going to reserve the right at the end of the semester to possibly slide those scales down by a notch or two, by a point or two. Maybe at the end of the semester, I find out that I was really tough this semester and not many people got 85 or better. Or maybe I had a real bunch of bad students in my class that semester, but I didn't want to give everybody Ds. Whatever. I want to push that grading scale down by a point or two. I may end up saying instead, at the end of the semester, 84 and above, 74 and above, 64 and above, or 83 and above, or something like that. But this is the strictest that I will be. Guaranteed. So what that means is if all of you score a final percentage of 85 or greater, you're all going to get A's in this class. I don't have any problem with that. Hasn't happened yet, but if it did, I wouldn't have any problem with that. Now, I'm not saying exactly how I'm going to do the pluses and minuses, but it's pretty straightforward. Let's take the range of B's. It's a 10-point range. In assigning B's, out of that 10-point range, what I typically do is the top 3 scores in that 10-point range would be the B pluses. The middle 4 scores in that 10-point range would be the B's. And the bottom 3 scores in that range would be the B minuses. Okay, that's the way I usually award pluses and minuses in the various ranges. Which also means when I say 85 and above for A's, I'm including A minuses there. Okay, don't be surprised at the end of the semester if you scored exactly 85 and ended up with an A minus. That may very well be an A minus. Probably the bottom 3 point scores in the A range would be the minus for the A's and be awarded A minuses. Everybody get a general idea, though, how I'm doing the pluses and minuses and letter grades? Okay. Once we're further along in the semester and you've seen a lot of homework scores and computer assignment scores and 2 of your 3 test scores and so on, feel free to come on up and ask me and we'll go through how you're doing in the class, what grade you're likely to be getting, and how well you'd have to do on that last test, and so on. I'd be more than willing to discuss all of that type of stuff with you in further detail. Okay, let's see, any other comments I can think of? How about questions on your part? Anybody have any questions on the syllabus or anything like that related to the course? Okay, you're sure to come up with questions later on. Feel free to interrupt me at any time or come see me after class or talk to me during office hours or whenever you can catch me, and I'd be more than happy to talk about this material in further detail. All right. Let's see here. I guess we're ready to start talking about class material. Before we get into the actual class notes, the Chapter 1 class notes, let's go through this handout, which is posted on the Blackboard site, and which I also passed out today, which I called Introduction, or Preface, as it is called here. And what I'm talking about on this one page is the basic rationale behind this course, why this course is an important course. Here's the problem. The basic problem is, as frequencies go up, standard methods of analyzing and designing circuits don't work anymore. You need to come up with some new ways of analyzing and designing circuits. Frequencies are going up. This is a trend that's not going to end. Not going to end anytime soon. Frequencies are steadily increasing. Think about frequencies of operation for things like computers and cell phones and mobile phones and remote radios and so on. Ever higher frequencies is what we're seeing. Why? Why are we going to higher and higher frequencies? Anybody have any answer to that question? For computers, yes. Data processing, the faster the clock speed on your computer, the faster it's going to be able to process that data. Absolutely. How about communication systems? There's another reason there, besides just data processing speed, which is important in communication systems too. But,
It reduces interference?
The what now?
Interference?
No, actually, that's one of the problems. Interference is one of the problems that you get at higher frequencies, and it only gets worse. We're going to talk a lot about that.
The use of the spectrum.
Yes, that's the key I'm looking for here. Using up the spectrum that's available, the bandwidth. The spectrum's fairly well utilized at lower frequencies, and if you want to find free range of frequencies that's not being used, you're probably going to have to go to higher frequencies. Not only that, but modern communication techniques are getting more and more frequency intensive. They're using larger and larger bandwidths for new communication protocols and techniques. Spread spectrum is exactly what it sounds like. They're using wide swashes of spectrum. And you have to go up to higher frequencies to find those increasing amounts of bandwidth. Okay, so back when I was going to school, the big buzzword for RF was gigahertz, and anybody who knew anything about gigahertz was a wizard. Gigahertz, that's 10 to the 9th. These days, the newest buzzword, if you want to get some funding or publish a paper, mention the word terahertz. People go nuts about that one. That's 10 to the 12th. That's 1,000 gigahertz. And they're starting already to talk about and design signal processing circuits and even talk about CPUs, computers, that work in these terahertz frequency ranges. As a matter of fact, satellite and some other communication systems, not frequencies, communication frequencies, as communication systems at these frequencies are already being used. Now, as I said, what's the problem here? The problem is as you increase frequency past certain limit or certain range, standard circuit analysis and standard circuit analysis software just plain old fails. Gives you the wrong answer. So, if you're going to be doing design and circuit analysis and simulation at these higher frequencies, you've got to come up with new methods of analysis. And you've got to replace those old software packages by new software packages that take into account the fact that now we're talking about higher frequencies. What happens at higher frequencies? That's what you were saying there. That's where you get that crosstalk. You get these radiation effects. You get wave effects in general. You no longer can think of voltages and currents as being the same at one point as they are at another point at any given instant of time. Because now, as the signal varies at one point in the circuit, it takes a little while for that wave to work its way down to the far end of the circuit. A finite lag there, a time lag. And so you get these wave effects that have to be taken into account. Radiation effects and wave effects start rearing their ugly heads. But they're not so ugly. Actually, we'll see how to handle them quite readily in this course. Okay. Now, remember I said that once you get past a certain frequency or past a given range of frequencies, you have to start using these RF techniques. Exactly what frequency are we talking about here, or what range of frequencies? Well, answer is, it depends. I can't tell you. There's no single answer to that question. And here's the reason. This is a pretty good rule of thumb for deciding whether you can use standard low-frequency analysis techniques and standard circuit analysis software, or if you have to start talking about RF analysis and software more like the ADS that we're going to be using in this class here for RF. And that is, if a typical dimension in the circuit that you're trying to analyze, if that typical dimension in the circuit is larger than a 20th of a wavelength, then you can't use low-frequency techniques. Then you have to start thinking about the stuff we're talking about in this class. Then you need to use RF analysis. So, if a typical dimension in your circuit is larger than a 20th of a wavelength, then that's where we come in. That's what we're going to be learning in here. What do I mean by a typical dimension? Well, it may be like the size of your circuit board when you lay it out on the lab bench. That might be a typical dimension. Okay, well, let's think about typical dimensions then for signals of different frequencies. All right, now it probably comes as no surprise that a signal at, let's say, 3 gigahertz is one that we have to use RF techniques to design a system that would use that type of a signal. Let's do the calculation. What's the wavelength at 3 gigahertz? Well, lambda is equal to c divided by f. Well, c is the velocity of propagation of light in free space. 3 times 10 to the 8th. That's what I mean by c there. And f is the frequency. By the way, the way the physicists usually write this formula is lambda is equal to v divided by f, where v is the velocity of the wave. I'm assuming free space, so the wavelength is v is equal to c, 3 times 10 to the 8th. But if I was in some other medium like water or Teflon or something like that, I'd have to use a different velocity of propagation. But let's make it simple. Let's just use a wave in free space. C divided by f. And plug in the numbers. C is 3 times 10 to the 8th. F is 3 times 10 to the 9th. So you come out with 0.1 for lambda. 0.1 meters. Let's see here. Divide that by 20. And you get 0.5 centimeters or 5 millimeters. That's what a 20th of a wavelength is at 3 gigahertz. Okay, that tells me that if I'm trying to design a circuit that has a typical dimension of more than 5 millimeters, I better use ADS software and not PSpice. And I better apply S parameters to the circuit analysis rather than just using plain old Kirchhoff's voltage law and Kirchhoff's current law. These are the things we're going to learn in this class. 0.5 millimeters. That's pretty darn small. That's a pretty tiny distance. 5 millimeters, 5 millimeters. Still, 5 millimeters. Pretty small. You know, the lead connecting one point in a circuit to a resistor is probably larger than 5 millimeters long. Definitely on a motherboard of one of these computers or in a cell phone or mobile radio or something, it's real easy to imagine that a typical dimension is bigger than 0.5 millimeters. So you have to make use of RF analysis techniques. So at that frequency, neglecting RF effects by using standard design techniques and standard software packages is going to give you erroneous results. By the way, we'll talk more about this. Any AC waveform is, strictly speaking, a traveling wave. Why don't we worry about traveling wave effects and wave effects in general when you deal with regular AC circuits in, let's say, circuit analysis 1 and circuit analysis 2, 3300 and 3301 and so on. Well, let's take a look at the type of AC that they are normally talking about in circuit analysis 1 and 2. That is a frequency not 3 gigahertz. Let's be reasonable here for electricians and talk about regular household voltage, current, AC, 60 hertz. In free space, the physics is still there. Wave is still a wave, and the formula still holds, and we can still calculate a wavelength. Only now, that's what we're calculating. That's a pretty big number. The wavelength at 60 hertz is huge. It's 5,000 kilometers. That's over 3,000 miles for one wave. for its wavelength. You'd have to have a pretty darn big circuit in order for it to be bigger than a 20th of a wavelength. Twentieth of a wavelength? I don't know. Right? Something like that. If it was 3,000 miles, then a tenth would be 300, a 20th would be 150. So it's a little over 150 miles. So if you string an AC 60 hertz from one point to another, don't worry about having to use ADS to analyze that circuit, unless it's a pretty darn big one. Pretty darn big one. Actually, back in the old days, back when Maxwell first came up with his set of equations to describe electromagnetics, nobody much worried about them except for theoretical physicists who had fun with them and mathematicians who loved playing around with these equations. And there was really only one practical application. We're talking mid to late 1800s. And that application was an application where people were hooking together circuits that were 150 miles or so long or longer. And they had to worry about the wave nature of these low frequencies. Who would that be? Well, I can think of two examples, actually. Who would be hooking up circuits that long? Wires that are 150 miles long. Power companies, you bet. FPL has to worry about the wave nature of 60 hertz AC signals on their power lines, at least on their long-distance lines, the ones that connect us to Atlanta and places like that. A set of equations that we're going to see real soon now is called the telegrapher's equations. There's no mistake in that name, because back before they even had power generation like FPL, they still had telegraph lines connecting one outpost in the prairies to another. And those telegraph lines carried signals that were varying in time, dot, dot, dash, dash, and telegraph and Morse code. They were 60 hertz or more, actually, because they were sending pulses. And as you know, pulses are pretty spread out in the frequency domain. They have some fairly high frequency components associated with them. And so the people who built and operated telegraphs had to worry about the wave nature of the signals that they were sending and receiving. So these equations were called the telegrapher's equations because it was only these telegraph men that were concerned with them, and they were considered the rocket scientists of their time. If you could understand and operate and know how to design and build these things, that was high science. Okay, enough said. Let's get back to the introduction here. Okay, so what are we going to do in this class? Well, of course, the solution to the problem is to come up with some alternative design techniques that take into account waves and radiation at RF frequencies, and to make use of software packages that take into account waves and radiation at RF. So that's basically our biggest goal in this course, is to introduce these design techniques and these software packages and use them in design of useful circuits like amplifiers. Okay. You're going to see this semester a lot of formulas, an awful lot of formulas that are pretty complicated formulas. And Some of these formulas you're going to be computing over and over and over using the same formula, changing one variable during each calculation. I find that a programmable calculator is a real handy thing to have. The next point is not just handy. This is a must. Almost every quantity and almost every formula that we're going to be working with this semester is in terms of complex variables, complex numbers. Complex numbers on one side of the equation giving you complex numbers on the other side of the equation. You have to know how to perform basic algebraic operations on complex numbers. In other words, you have to know how to do addition, subtraction, multiplication, and division of complex quantities with both hands tied behind your back. It's got to be that familiar to you. You have to know how to do conversion from rectangular form of a complex number to the polar form of a complex number, back and forth, polar to rectangular conversion, and so on. So, brush up on that. You're going to need it. These formulas that I was telling you about in the first point there are almost all in terms of complex quantities. And the calculator that you use is going to be a lot more useful to you if it is able to handle complex numbers. I've got here a handy little programmable that I've been using for many years now that supports complex mode. And I've got just about every formula I use in this class programmed into that calculator, and I use it all the time when I'm cooking up problems for homework assignments and tests and when I'm coming up with examples and so on. I find it real handy. These days, students are as likely as not to have a notebook computer available to them. So rather than using a programmable calculator with complex mode, a PC running a spreadsheet program like Excel will do just as well. It's a little bit more cumbersome in that Excel doesn't handle complex numbers per se. But you can always break your calculations up into a real part and imaginary part. And whenever you have an equation saying one complex quantity equals another complex quantity, that means the real part of both sides of the equation is equal, and the imaginary part of both sides of the equation is equal. So you can break that single complex equation into two real equations, one equating the real parts of both sides and one equating the imaginary parts of both sides. So spreadsheet programs like Excel can be used to do a lot of these calculations. As a matter of fact, I've come out of the dark ages. I have actually programmed an Excel spreadsheet to do all of the same calculations that my programmable calculator does, which is to say all the main calculations that are necessary in this class. I will make this spreadsheet, this Excel spreadsheet, available to you bit by bit throughout the semester. As I introduce a new equation used in design, the first time we go through it, we're going to go through it by hand and do some calculations by hand with that equation. But once we're done with that section and we move on to a new topic, more often than not, we have to be able to do that old type of calculation first before we can do the new type of calculation. The stuff in this course is cumulative. It builds on itself. So once we move on to the next section of material in the course, maybe then I'll make available to you the part of the spreadsheet that did the calculations for the previous part. But I want you to have the joy of doing those calculations by hand, or at least by yourself with a calculator or computer, without the aid of my spreadsheet at least once or twice before you make use of my spreadsheet. Biggest reason for that is garbage in, garbage out. If I just gave you a computer program and you didn't have any idea of what it was doing inside, and all you knew how to do was type in a number at the input and get a number at the output, you'd have absolutely no way of knowing whether what you come out with is pure gibberish or whether it's a sensible answer until you've gone through the process of doing the calculation once or twice yourself and seeing what a reasonable answer should look like. Some of you may want to use a computer and a spreadsheet or a calculator as programmable to do those calculations before I give you the spreadsheet that I have that does those calculations. Feel free. If you want to program those equations yourself and make use of a program to do those calculations before I provide you with my own version, go ahead and do that. Make use of whatever computing power you have at your disposal. The experience of programming in those equations yourself is just as good as the experience of having to calculate them all through by hand once or twice. Okay, you'll learn more about the equations just programming them than you would in simply calculating with them, as a matter of fact. All right, well anyway, a lot of calculations, and I'll try to make it easy on you once you have done the calculations once or twice yourself. Okay, we're going to be doing a lot of work with transmission lines all the way through the semester. You're going to need that material from Fields and Waves class. Transmission lines, specifically. And, even more specific, Smith charts. You all remember the Smith chart, right? Remember the old Smith chart that you saw the last lecture or two in Fields and Waves class? Okay, you're going to need these. I have this in PDF form posted on the Blackboard website. It's called smithchart.pdf. You can download as many as you like and print them out. There's another type of Smith chart that we're going to be making use of called the YZ Smith chart. It's this colorful thing. You can't see it as well on the overhead, but it's red and gray, red and blue, rather than just black and white. It's two Smith charts, one of them rotated by 180 degrees and then plopped down on top of the other. You're going to need both kinds of Smith charts. This so-called YZ Smith chart, the more complex one, that's on the web as well, on the Blackboard website, under the title YZ Smith chart. Download it and print it out. Let's see here. One of the things that we're going to be using a lot in this class are the scattering parameters. We're going to do our circuit design primarily in terms of scattering parameters. Scattering parameters, they're sometimes called S parameters. You've no doubt heard the term before. You're going to get a good introduction to scattering parameters and how to make use of them in analysis of RF circuits in this class. As a matter of fact, that's one of the goals of this course, is to get you up to speed on the use of scattering parameters. Okay, any questions here? Okay, if not, we're ready to move on to the class notes. The first chapter of the textbook is entitled Representation of Two-Port Networks. And we're going to be making use of two-port networks an awful lot in this class. By way of introduction, here is the general circuit symbol for a two-port network. Here's the box, the black box. That's our two-port. It has terminals, two of them, on port 1, which is the port over on this side. I sometimes call that the input port. And here are the terminals on port 2, which I sometimes call the output port. I really shouldn't use the terms input and output for those two ports because you could just as easily hook a source up over here and a load up over there on port 1. It doesn't really matter which you use as input or output. The thing to pay attention to in this representation is the polarity of the voltages that are defined at the two ports of this two-port network and the current directions associated with the currents flowing into the two ports of the two-port network. The voltages have the same polarity, plus at the top terminal and minus at the bottom terminal, plus at the top, minus at the bottom. That's the convention for the voltage. The convention for the direction of current flow, on the other hand, is current flow for any port on a two-port network is defined as the current flowing into the top port. So I1 is defined as the current flowing into the top port, the top terminal of port 1. I2 is the current flowing into the top terminal at port 2. Okay, two ports are handy things to define when doing circuit analysis because that two-port, as I mentioned, you can think of it as a black box. It can contain an arbitrary number of components hooked up in any arbitrary fashion. Anything you want, hooked up in any way you want, inside of that black box. We just choose 2 points over here to represent what we're calling port 1 and 2 points over here that we're calling port 2. But inside of that black box could be 6 resistors and 3 capacitors and 2 inductors all hooked together in some very complicated fashion. So the two-port is a general representation of what could be a fairly complex circuit. However, we're assuming when we draw the two-port in this fashion as this black box that we don't care what happens inside of the two-port. We don't care what happens to each and every one of those 6 resistors and 3 capacitors and 2 inductors. There are only 4 variables that we're interested in. We're interested in the voltage V1 defined here and the voltage V2 defined here and the current I1 defined here and the current I2 defined there. There are many, many other voltages and currents that are possible depending on the exact configuration of what's inside of that two-port, but we're not concerned with them. We're only concerned with the voltages and currents that we see at the 2 ports of our two-port network. In circuit theory, circuit analysis 2 usually, the two-port network is discussed. And they talk about 4 different parameter sets that you could come up with to describe the two-port network. That is to say, to describe the relationships between V1 and I1 and V2 and I2. Those are the Z parameters, the Y parameters, the H parameters, and the ABCD parameters. Turns out that there are 4 of each of these parameter sets, and they're usually represented as 2 by 2 matrices. 2 rows, 2 columns, 4 elements in all. Now, these nice parameter sets at low frequencies don't work so well at high frequencies. As a matter of fact, the parameters that are used at low frequencies are really not even suitable at higher frequencies for a number of reasons that we'll talk about in just a moment. A new parameter set called the S parameters, the scattering parameters, is more suitable for work at high frequencies. Just like the low frequency parameter sets, there are 4 scattering parameters, and you usually form a S parameter matrix, a 2 by 2 matrix that contains those 4 scattering parameters. Okay, if you want to see conversion formulas between the Z parameters, the Y parameters, the H parameters, the ABCD parameters, and the scattering parameters, all 5 parameter sets, you can find them in the book. They have one table here, pretty nasty looking little table here, that tells you how to convert from one parameter set to the other. So this is a great thing for programming into a computer. You can do it by hand if you have to. That is to say, if you're given the Z parameters of the 2-port and you want to do some high frequency analysis, you need the S parameters, you can do a conversion from Z parameters to S parameters. Definite formulas there. That'll do that for you. And the opposite. You can convert from scattering parameters back to the low frequency Z parameters. Okay, let's talk about the different low frequency parameter sets. This will serve as an introduction to the scattering parameters that we're going to be making the most use out of. Okay, the first thing that must be assumed when defining these different parameter sets is we must assume that the network, whatever it is inside of that black box, is a linear network. It can contain any arbitrary devices at all, and any number of them, and in any arbitrary connection, as long as the devices are linear devices. If the devices contained inside of a 2-port are all linear devices, then mathematically you'll find out that the relationships between V1, V2, I1, and I2 always turn out to be mathematically linear relationships. That is to say, there's a nice linear relationship between voltages and currents at the 2 ports of our 2-port network. And depending on how you write the linear relationships, depending on exactly what form you write them in, that'll tell you which set of parameters you're dealing with. Okay, here's the two-port network. Let's say that we wanted equations for the currents I1 and I2 in terms of the voltages V1 and V2. What I'm saying is exactly the opposite. Let's start with the Z parameters. Let's say you want V1 and V2 in terms of the currents I1 and I2. V equals IR, after all. V equals IZ. Here we go. Here's what the relationships should look like. A linear relationship. V1 is some constant times I1 plus another constant times I2. That's the most general linear relationship you can possibly write for V1 in terms of I1 and I2. You can write a similar linear relationship for V2 in terms of I1 and I2, where you have two different constants, Z21 and Z22. Well, you can see from the notation there that I'm getting ready for a matrix form of that equation. There's the matrix form of that same equation. Z11, Z12, Z21, and Z22 are the elements of the so-called Z parameter matrix. That's the Z matrix of the two-port. And of course, this matrix equation for the column vector V1, V2 in terms of the Z parameters and I1 and I2 column vector is exactly the same as the two original equations, right? You'd get one equation from the first row by saying V1 is equal to I1 times Z1 plus I2 times Z12. That's exactly what we have. And V2 would be I1 times Z21 plus I2 times Z22. Exactly what we have there. So that's the matrix equivalent of that linear relationship. However, you could say you wanted the exact opposite dependency. Let's say you wanted equations for the port currents in terms of the port voltages. So you're treating currents as the unknowns and voltages as the knowns in this second case. Well, then, the most general possible form of the linear relationship that would give you the currents in terms of the voltages would be written in this matrix form. I1 is equal to V11 times Y1 plus V2 times Y12. I2 is V1 times Y21 plus V2 times Y22, or this matrix equation involving the admittance matrix, the Y matrix. In matrix form, there's a nice relationship between the Z parameters and the Y parameters. What is that? If I gave you the Z matrix, how would you find the Y matrix? What would you do to the Z matrix? Yes, all there is to it. It's the inverse matrix. The Y matrix is the inverse of the Z matrix. You can actually show that by solving this matrix equation for I1, I2. How would you do that? Pre-multiply both sides of this equation by the inverse matrix of the Z matrix. That would give you the identity matrix here, or just I1, I2 on the right-hand side, and it would give you the inverse of the Z matrix here times V1, V2. But that's exactly what we have here. I1 and I2 on one side, V1, V2 on the other side, multiplied by a matrix. That must be that inverse Z matrix. Okay, those are the most common ways of writing the relationships between voltages and currents at the two ports. But there's a couple others. There are the hybrid parameters. For the hybrid parameters, we assume that we're given the current at port 1, I1, and the voltage at port 2, V2. And the other two are the unknowns. That is to say, the voltage at port 1 is unknown, and the current at port 2 is unknown, and we write them as linear combinations of the two known quantities. Well, here it is. That's the mathematical expression giving a linear relationship between I1 and V2 and V1 and I2. There we go. And the coefficients in that linear relationship, those are the H parameters, the hybrid parameters. And that matrix in this equation, that's the H parameter matrix. Those are the hybrid parameters that are typically used for electronics, used for transistor circuit analysis and design. That's not the only way you could go about it. Here's another possible combination. Let's say V2 and minus I2 were the known quantities, and we wanted to solve for V1 and I1. Then the most general linear relationship that you could write would take the following form as a matrix equation, where we've got a matrix of coefficients. These are the A, B, C, and D coefficients. That's the ABCD matrix altogether. And it's a useful way of relating port voltages and currents together, because it gives you voltage and current at port 1. These are all quantities on one side of the two-port device, at port 1, given in terms of the corresponding qualities at the other side of the two-port, at port 2. You could think of this almost like a transfer matrix. It tells you how voltages and currents at one port transform into voltages and currents at the other port. By the way, there's a reason for putting a minus on here in my definition for the ABCD parameters. And we'll see that reason soon enough when we get to interconnecting two-port networks together. However, we're about out of time. And if I could do one more thing here on the overhead. You see that? I am out of town on Thursday, day after tomorrow, but never fear. Tomorrow morning, 9 o'clock, I will be here recording a lecture. So I won't be here live in person, but you'll be in here watching the screens. Those of you in the library and distance sections won't notice